I would if I could. That's one problem with virtual meetings.
Yeah.
Can't have cake.
By the way, if you want a little bit of humor, Google XKCD and before pandemic.
Okay.
And it's a few totally ridiculous things about life before the pandemic, things I miss.
Yeah.
Indoor fireworks.
Yeah.
Tennis without that silly safety net between the players.
Yeah. Yeah. Jeez.
Last week is a tough act to follow, boy.
Yeah. Well, Dan, yeah, that was pretty interesting, actually. I thought Dan did a really nice job. He's very loquacious.
Yeah.
Well, I get to practice it twice a semester with my wife's nursing class. Although a little bit more in depth with you guys, I skimmed across the real easy stuff. And
where does your wife teach, or is she a student?
She runs a department of nursing at FDU in Florham Park.
Okay, because I also taught nursing.
I know that, yeah. So
yeah.
In what park?
Florham Park down in Madison, New Jersey.
Oh,
so it's a branch campus.
Yeah.
Well, I love to ask the nurses, the nursing students, what a drug is, and you'd be amazed how long you have to sit there, the uncomfortable silence, while they try to come up with an answer for what a drug is.
I had a lot of foreign students, and that was very interesting to look at what they knew and didn't know, depending on where they came from.
She's actually told me that some of her students from Haiti believe in voodoo. They actually have some fear of voodoo and curses and the evil eye and things like that. And that's a little scary.
Well, if you dive into anybody's traditions, they can all look pretty odd to somebody that is from a different tradition.
I agree, but to actually believe in it and to fear it and think that somebody could put a hex on you or a voodoo hex, a little bit, at some level, you got to drop that stuff if you're going to be an objective.
Oh, well, yeah.
Caregiver.
Some years ago, a colleague and I, Steve will know this, is Bruce Schneider, we thought for the Journal of Irreproducible Results, writing a fake FDA application for water as a thirst quenching drug. This is the minimum daily requirement. This is the lethal dose 50. If you drink a lot of beer, you should accordingly reduce your water intake.
I can see that, but what would you use for placebo?
Alcohol, of course. That was easy.
It would be very well blinded.
All right, we're going to get started here. Harold Hastings is going to be talking tonight, and he's going to be talking about fractals. And that's my phone ringing in the background, but don't worry about it. Harold loves science, teaching, and the outdoors. He has degrees from Yale and Princeton, and now lives in the Berkshires. They're hills by Western standards. And he teaches Bard College at Simon's Rock. Like Scott and Scotty, he frequently relaxes by reading science when not hiking and building. A recommendation from him is Scott Aronson's Quantum Computing Since Democritus. Okay. Harold, it's called Taming the Mathematical Monster, Fractals in Science and Art.
So can everyone see the PowerPoint?
Yep.
Okay. There are a few times I'll want to write on it, so I think let's see if presentation mode works here, and we may switch once or twice. So
hold on.
So you should have a screen now that's just the full screen, Taming the Monster.
Got it.
Okay, and there's a fractal tree. And in fact, when you draw a tree and you draw a trunk and branches on branches, as we all learned back in kindergarten, you're in fact drawing a fractal. So this is sort of the mathematical origin. Way back, well, not so far back, the middle of the 19th century, people thought of functions that were not smooth, in fact, were nowhere smooth, as being mathematical monsters, perhaps out of the range of appropriate study by civilized mathematicians. So you could have a few corners, but this video at the back where it looks to be all mountains was thought of as a mathematical monster. This is Weierstrass's continuous nowhere differentiable function. And in fact, there'll be a little math here and hopefully not too scary. But if I build a sequence of waves, this is a Fourier series, a very simple one to people who recognize it. And there's a condition that if the coefficients get small fast enough, it converges and represents a function. On the other hand, if I take the derivative, the cosine of nx, this n here, shows up as an additional coefficient. And so now the coefficient of the nth term is NaN. So that doesn't go to zero necessarily. In fact, it may not, it would have to go to zero sufficiently fast to get a smooth function. So I can get a well-defined function where, because the wiggles taking place are taking place at such high frequencies, it's kind of all corners and bumps. So this was thought of as a mathematical monster. And there are other examples too, but this was a time when people thought of the world as nice and smooth, or at least mathematics was there, and so the question is what's going on? So just let me do a little drawing first, and I'm going to suggest to people that you imagine drawing a face and drawing a tree, and I'm pretty crummy on the computer drawings, but I will try it, and you can laugh for a while. So if I want to draw a face, I might start with a circle or an oval. This will not be necessarily great. And I might add some eyes. And so let's see. Now let's undo that, put it more where it ought to be. And I could add some other things, but essentially I'm using smooth shapes typically to draw the face. Now you can see why I'm not an artist. On the other hand, think of asking, how do you draw a tree? Well, there are various ways to draw a tree, and I can't get the thickness right here easily, but I might have a trunk, and there are branches off the trunk, and there are branches off the branches. I can do this in a regular or a random way. I can write down mathematical rules for the short branches versus the long branches. But this is described nothing like drawing a face. This looks a little like you've got a combination of irregular things on a wide variety of sizes. And in fact, one of the questions you could ask is, what's the appropriate math to describe these things? And how do they exist and how do they come to be? And you could draw other things that look complicated and irregular. You can draw the axonal processes of neurons. that branch way out. You can draw the lung in biology. You have these structures that are here, and you might even ask, how hard is it to make one, the genetic instructions, but I could draw a tree. This is a very tiny tree. And then when it grows bigger, maybe it branches more. So I could have a grow and branch procedure that takes very few instructions to in fact produce a rather complex object. But the point I just want to make here right now is that the mathematics of these two is a little bit different. And the mathematics of things like trees is going to lead us into fractals. And by the way, if there are any questions at any time, please just unmute, and I'll try to pause frequently because it's hard to watch other parts. But this is just a picture of the difference between the geometry of maybe pictures of the human form. That's the amount of hair I'll have in another 5 years. And at least frameworks for trees that you would put some branches on. So I need to get rid of these. And I need to get rid of that. Yeah. It looks like I've crashed something. Oh, here I am. So here are some observations. Just a minor comment that the Henry Moore Foundation requires that I have reproduced by kind permission of the Henry Moore Foundation when I publish this photo. So very British. But we have a bunch of trees existing. Here's a fractalish pine tree, and here's an idealized human form made up of smooth geometric objects. So there really are almost two sorts of geometry. There's the geometry of smooth, regular objects, and we'll allow ourselves a certain amount of corners here. I mean, we're not going to rule out squares and rectangles and cubes and triangles, but much of the components then are either, they're built of a finite number of components that are either lines or regular things and smooth curves. So we can compare an idealized human form drawn out of some smooth objects versus fractal trees. So what math? How do you discuss the two things? You learned a lot about the circles, areas pi r squared, circumference is 2 pi r. You know how to measure them. I mean, we saw that math way back in junior high school and earlier. And what's the appropriate math for the other stuff? So that I want to look on a little bit. So I'm going to draw some fractals. And these were originally looked on as mathematical monsters. The Koch snowflake from a mathematician, Helga von Koch. Von Koch, this I think was late 1800s. This used to be fun to give around New York City and for people in New Jersey when there was the snowstorm that undid Mayor Koch in New York. And I used to jokingly say this was the Mayor Koch snowflake. But here is a snowflake that's made, and it's made rather simply. I take a triangle. I replace each straight edge by putting a bump on it. So the new form you can see is this picture here. And the original figure under it is in green. And then I put bumps on the bumps and bumps on the bumps. And I keep going until I reach a limit of resolution. And it produces a complex geometric pattern. And it seems like, and we could ask, it seems like it's a long way around. If I have to get around this with little tiny steps and follow all of it, it's a very long way around. This is the Cantor set from a mathematician and logician, George Cantor. And it also was designed as a pathological object. The way you construct it is you start with a line. Now, they've made it a bar, but think of this as drawing a line. And then you erase the middle third of the line. So now if I erase the middle third of the line, I get a smaller line here and a smaller line here. And I erase the middle third of each and the middle third of each of those. And it kind of seems like there's nothing there, you know, so what is this? And for people who've looked at history of math or advanced math in college, I mean, this was sort of posed challenges to people working in measure theory. So in fact, I'm going to try to measure these things. And that's where some of the new mathematics will come in. And the question I'm going to ask about the Koch snowflake, how big, we could ask about the area that's around, the perimeter, and the dimension. Well, the area is clearly finite because come on. This snowflake, no matter what I do, I can find a big box that it will stay within. The perimeter is another question, and we could also try to ask about its dimension. I mean, this boundary is a curve that has corners everywhere. I mean, how do I kind of think of it? It doesn't look anything like a line or a smooth curve. And I could ask the same question for the Cantor set, which seems to disappear. So let's try to figure out the perimeter of the Koch snowflake. And I'm going to make the length of one of these sides 1. So the perimeter of this is 3. So this is a unit length. And now what I've done here is I've taken 1/3 of each side and I've replaced it with this bump structure. This is an equilateral triangle. So this side is now 1/3 plus 1/3 plus 1/3 plus 1/3. There are 4 pieces where there used to be 3. So I'm adding 3 more bumps, 3 extra thirds to it. The perimeter of this is 4. It's 4/3. You can just calculate that. And it's fact, I'm going to think of the 4 as the original 3 times 4/3. And now on each of the straight lines here, I stretch it by another 4/3, another 33%, and draw these bumps. So I again multiply by 4/3. And I keep multiplying by 4/3 forever. So 3 times 4/3 times 4/3 times 4/3 keeps getting bigger. In fact, that has a mathematical limit. It's infinite. There is no reasonable definition of length that makes this length of this finite if you give me the ability to measure on an arbitrarily small ruler. Now, I think the physicists might be upset because, yeah, at the Planck scale, it breaks down and we can't do this forever. But I mean, in theory, this well-defined curve, you can check that it's well-defined. You can formalize it. It lies in a bounded region. You see my cursor moving around? Yeah, lies in a bounded region, but it's got an infinite perimeter. And in fact, Richardson asked in a famous thing, how long is the coastline of England, Britain? I think it was the whole Britain. And, you know, it depends. If I'm able to take giant steps, it looks smaller. If I could take steps of length 1, I can get around this in just a few steps. If, on the other hand, a little kid can take tiny steps, they have to take an absurdly large number of steps. So this certainly looks a little bit weird. The perimeter is infinite. The Cantor set, how big? Its length in, well, let's see. Let me call this length 1. I get rid of 1/3, so I multiply the length by 2/3. This has length 2/3. This is 2/3 times 2/3. And each piece, if I add up all the little bits, it's 2/3 times 2/3 times 2/3 seems to go to 0. If I try to look at the length, it's 0. And if you think of the Lebesgue measure on this, it's 0. The foundations of integration of some of these wild functions with Carat-Theodore and Hausdorff and so on, it made sense to assign it length 0, but you could play a funny trick and look at how many points there are. I mean, if I look at this, I could think of points. I'm going to pretend I have binary numbers, but I'm going to make ternary numbers, three different digits, 0, 1, and 2. So this is first digit 0, first digit 1, first digit 2. I'm the first third, the second third, the third third. Now here, it's again 0, 1, 2, 0, 1, 2. So when I cut out the middles, I'm getting rid of all the numbers which have 1s in the middle. I've got numbers made of 0s and 2s. Pretend they're made of 0s and 1s. Turn all the 2s into 1s. I've got all the binary numbers from 0 to 1. There's a lot of stuff that's still left, despite the fact that the length is 0. So, I mean, this initially bothered a bunch of mathematicians that were around. This didn't seem to fit in with logic at roughly the 1900s. If my brain explodes, by the way, I'll give you the local 911 contact from the fact that my logic gets limited. But these appeared to be things that violated what looked like the rules of mathematics. So I'm going to try to think a little bit more about dimension, but let me mention a little bit of history on this. Henri Poincaré looked at the motions of complex things. It turns out that once I have a system of 3 objects, like the sun, the earth, and the moon, or the sun and Jupiter's moons, then I can generate very complex motions. The motions can become highly irregular. And for example, if you look at asteroids, and the period of Jupiter is 12 years going around the sun, and it's actually a little less, but let's call it 12 years. There are essentially no asteroids which take 6 years to go around the sun, because they have a resonance with Jupiter, and Jupiter will deorbit them. It will transfer energy to them. The motion in this case, in fact, is called chaotic. And people began to realize that lots of things were, in fact, chaotic. What limits our ability of weather forecasts? I mean, typically the Weather Service gives you 6 to 7 days. Channel 9 may try to give you a 9-day forecast, but Channel 93 doesn't try to give you a 93-day forecast. No one can do this. And in fact, we use more and more powerful computers to get where we're going on this. Japan has the Earth simulator. We have a giant IBM computer in Knoxville, Tennessee. Computers that'll have the equivalent of 100,000 or 1 million PC processors in them. And we're still limited by something fundamental, that a small initial error in measurement or parameter in the model ultimately causes things to blow up. And that's sort of a little bit of chaos. If you had an upbringing in college which had you trying to play pool, what you discover is you can make shots typically of a certain number of caroms, but then suddenly you can't make them at all. And in fact, every time you get a collision, any small error in angle doubles. So at some stage, depending how precise you are, you're still out of luck. But let me come back to dimension, and I'll ask, why is a cube 3-dimensional? Well, let's see. The formula for a volume of a cube is the side cubed. Well, what's volume? Well, let's see. If I take for example, a 5x5 cube, Well, let's ignore that one. If this is a cube of size 5, and then I look at a unit cube, it's hard to draw dotted lines where I should, but this is a unit cube. It takes 125 of these to fill the big cube. It takes 5 cubed little cubes to fill the big cube. And the dimension is just an exponent. If I count the little cubes, the number of little cubes to fill a big cube of side S is just S cubed. And we call 3 the dimension. I can look at this the other way. I can kind of zoom down. I can pretend this cube here. Oh, come on. I don't want that. I want the eraser. Goodbye. Let me make the side of this now 1. Pretend it's a cube of side 1. And let me make this little piece, let's just call it 1/10. So how many cubes of size 1/10? If I shrink the big cube, honey, I shrunk the cubes. If I shrink the big cube to be 1/10, it takes 1,000 of them to fill the large cube. So if I shrink them by a factor 1/n, the number it takes again is little n cubed, and that's the dimension which I'll loosely call a similarity dimension. It's one of the fractal dimensions, and it's in many cases equal to what's called the Hausdorff dimension. And I don't know if any of you have read Benoit Mandelbrot's books or heard him speak, but he tries to get all this stuff right. I remember talking with him, and actually Karateadori beat Hausdorff by about 5 years, but Hausdorff's publication is more famous. So one time that I used this in publication, I made sure to credit Karateadori, 1909. But this is a picture of dimension. And if I take a square, I get the same picture. If this square has size 1, and I fill it up of little tiny squares of, say, size 1/10, the side, well, you say, why are you measuring the side? Oh, no, I'm just taking the big square, I'm shrinking it. Shrink it to 1/10 its original size in all directions. Apply what's called an affine transformation in fancy terms, but just shrink it. Put it in the washing machine, like t-shirts that shrink. Only this is going to shrink to 1/10 its size, and it takes 100 of them to fill the square. And in general, if this were 1/n and not 1/10, then it would take n squared to fill it. So that's 2-dimensional. So here's the dimension. And this, by the way, agrees with the dimension for regular objects from linear algebra and so on. So there's the dimension. There's too much around, so I got to clear those. Get rid of that. Yeah. So here's the Cantor set. Here's the big Cantor set. I shrink it to 1/3 its size. And this is the sense in which you could allow other shrinkings here only by those factors in this scale and your similarity dimension. And there are 2 of them. So shrink it by 1/3, I get 2. 2 versus 3. 2 is not 3 to a whole number power. Something's not working right. Shrink it again by another 1/3. There are 4 of them. 1, 2, 3, 4. And in fact, if I shrink it by 1/3 to the nth, if I go down n stages, there are 2 to the nth little cubes. And whether I use 2 as the number of, we could equivalently make up, didn't mean unit cube. We could make up a Cantor set. So I won't retype it. we could make this Cantor set up of 2 to the nth smaller ones, each shrunk by a factor of 3. So I can make this up of smaller ones. If I do one shrinking, 2 is 3 to an exponent. I can calculate that exponent with logarithms, and I get 0.63. If I shrink it twice by a factor of 9, I get 4 pieces. 1, 2, 3, 4. 4 is 9 to the 0.63. If I shrink it again, 8 is 27. I mistyped this. 8 is 27 to the 0.63. The dimension is 0.63. It's not a constant. It's not an integer. It's not a whole number. The dimension, in fact, this isn't even a fraction. It's actually an irrational number. But the dimension is not a whole number like we're used to. And yet, this is the only reasonable number for the dimension. So this bothered the mathematicians at first. I thought dimension was a whole number. I went back to my elementary school teacher and got mad at her or him and said, you told me it's a whole number. And now if I divide this up into 81 pieces, I get 16 Cantor sets, and 16 is 81 to the 0.63. And I can take a limit to where I go way down to these little tiny pieces here, and I keep getting dimension 0.63. So I can have objects where the only sensible number for dimension is not a whole number. And now I can begin to understand a few more things. So I want to look at the Nile River level, and actually the British sent someone named Hurst out to explore the levels of the Nile River through time for surveys leading to the Aswan High Dam, and the US and Britain and France were going to build this for Egypt at the upper Nile. And then came the war in 1956, and Egypt closed the Suez Canal to navigation, and the US and Britain and France didn't build it. And it turns out we did the right thing for the wrong reasons. Russia built it later, and it's been an unmitigated ecological disaster, an unmitigated disaster on agriculture. That could be the subject of another talk. But I'm going to just talk about water levels. And in fact, the Egyptians kept careful records of the height of this, and the 7 lean years and 7 fat years description from the Bible is a reasonable one. This is something called a Nileometer, a meter for measuring the Nile. You can actually look up Nileometer in Google, and this is the picture of one near Cairo. What it is there's this large pillar. Now they've blocked the water from getting in, so you can now you can look at the pillar way down. But this was buried, and water from the Nile flowed in, and there's some marks on the pillar that represent the height of the Nile. And if the Nile had a good height in the middle, then it was good for agriculture. It flooded appropriately and spread out silt, making the land near the Nile fertile, but it then receded. If it was too low, it was dry and you couldn't grow things. And if it got too high, it was also bad because you could get severe flooding. And here's a picture of the water level in the Nile over a long period of time. Many people have quoted this. This is just where I got this from. They cite a database, but that database doesn't seem to exist. These are the fluctuations in height of the Nile. And then this is the integral, the cumulative thing. If you're building a dam, you might say, I need to store this much water to prevent flooding, and so I can release it in the dry years and so on. And the heights above some arbitrary mark tended to average around 12 meters. They used a somewhat different scale where the typically good numbers were around 10 to 14, 8 to 14 cubits by 18 cubits of height above some nominal mark. You had severe flooding, and down here you had droughts. And it kind of looks like this clusters more. You get these low years together, you get some high years together. This doesn't really look like I flipped a coin and said heads is a good year and tails is a bad year. And if I look at the cumulative water level to figure out how much I need to store, this looks a little too smooth for the trajectory of a random stock price or something. It's or a gambler's cumulative stuff. So Hearst studied this. This was a recent report on it that had this picture. And I'm going to digress briefly to discuss Brownian motion. Random walks. Brownian motion is the continuous version. So what you do is you get a coin. Don't try this at home. This is a thought experiment. You get a coin, and if it's heads, you move one step to the right. If it's tails, you move one step to the left. And you keep track of your progress. And you sample it maybe every 10 flips or 100 flips or whatever. And so I periodically sample it, and delta y is the distance I moved when I sampled it. And maybe you sample it every 10 steps, and I sampled every 100 steps, someone else every 40. I mean, different numbers, but we could ask about these, the story of these increments and what they look like. So turns out they're easy to characterize, and lots of people have seen them in statistics. They're independent. If I flip a coin, the results of one toss do not affect the results of the next, unless you cheat a little. I mean, it's in fact a deterministic process. And when I teach this, I usually try to sit quietly in my office, and I can flip a coin through 360 degrees repeatedly. And I'll say, what would you like, heads or tails? Watch. Tails, okay. Tails. What would you like? Heads. Turn the coin over. So it's heads, up, flips through 360 degrees, and show them heads. And I do this a number of times and say, look, it really is a deterministic process. A good magician could do this with many more rotations than one whole one. But it looks random because, in fact, it's unpredictable given the ability of most people to toss a coin. And if you tossed a coin and just tossed it up a little bit like this, they'd say that's not a legitimate toss. It's a deterministic process where the results of each toss are independent of the one before, because small fluctuations can decide whether it's heads or tails. And it's one of these things, if you could repeat exactly the same wind, humidity, temperature, muscle tension, same amount of coffee for breakfast, for the nurses and MDs in the audience, the same blood pressure, you know, whatever. If you could repeat everything exactly, it would do the same thing. So they're independent. It turns out they're identically distributed. If each increment comes like this, they all have the same distribution. It's a normal distribution. It's a bell curve. It's whatever you want. Its variance, the typical square of the size, is proportional to the time. Roughly speaking, the size is proportional to the square root of time. And some of you may be familiar with this in polling, that you got to poll a lot more people to get the results more accurately, or even some of the discussion of power in studies and how many people you need in order to narrow the spread from random fluctuations. If you want to cut the spread in half, you need 4 times as many individuals. So what's happening with, if I begin to say, I'm going to get rid of the independent assumption, oh, this ended up in the wrong place. this line should have ended up at the independent. So let me do this. This is going to bug me. There you go. I cross off the independent. In other words, what if each toss depended on the previous toss? What if there's a correlation? What if they're long-term correlations? So if the increments are independent and identically distributed and Gaussian and mean 0, but the variance depends on the time to some exponent. This is not the Hastings exponent. This is the Hurst exponent. Hurst understood, use H for the exponent. It will be named for you. Don't use like S for scaling exponent. And if anyone, by the way, remembers Banach spaces in college, Banach's original paper, he talked about spaces of type B. There are no spaces of type A. So B became the letter used. Anyway, here's this picture. And if H is a half, 2H, 2 times a half is 1. I'm back here. Loosely, the variance is proportional to delta T to the H. So if H is, for example, 0.7 and not 0.5, the swings are larger. The curve tends to reverse less often and the swings are larger. And if the correlation between increments is R, independent of the length of the increments, you can get some math that relates it. And this is called fractal Brownian motion. Now, this may look a little arbitrary, but this, in fact, was the story of the Nile. That if I come here, there's a fractal exponent here that's about 0.7, a Hurst exponent. And that characterizes this. So I can describe this curve and the fluctuations with this exponent. So there's actually an application of fractals to this science. And then this led to an ability where you said, if I need to be able to store so many years water on average, this is the size dam I need. Now, it turns out there are other cycles in here, and a student of mine, John Nielsen, and I, we calculated some other cycles here. And how do you calculate the exponent? Gee, this sounds really hard, but it's actually easy. What I do is I take increments of various sizes times what's the typical integrated water level change over 1 year, 2 years, 4 years, 8 years. And I look at those changes, I look at the delta Ys, I look at the delta Ts, and I just calculate an exponent. How are we doing? Oh, we'll finish comfortably within time. I don't know what this is. Is there a chat question? Chat, hang on 1 second, please. What's the question in the chat? It's hard to get it with my screen shared. Must be a way to look at that. Where are the controls?
I'm not seeing anything in the
Yeah,
chat.
I don't see a question on mine either.
Okay, thanks. So fractals in natural science, they're everywhere. Actually, with George Sugihara, who's a rather brilliant mathematical biologist that I met, and we met in kind of the heyday of fractals in the early 80s of the last century of the last millennium. User's Guide from the Natural Sciences. So with a number of colleagues here, we have a few papers on patterns among pancreatic islets. This is actually done from a microscope slide of taking some guinea pig, taking a slice of the guinea pig's pancreas after the guinea pig has been euthanized. And then looking at the positions of islet centers. And to simplify the picture and the analysis, instead of showing you a stained slide, I'm just showing you a dot as each center. and they look like they cluster. They almost look like they lie along some pathways. They're not random points in the plane. They're random points in a lower dimensional part of the plane. I mean, suppose I had houses along a road and nothing near it. Come to Sheffield, where when the road gets cut between my nearest neighbor and myself, to the east, a quarter-mile walk becomes a little over 4 miles as the way around the block. And if I look at the density of houses, I really have to describe it as lying along the roads and not everywhere throughout Sheffield. The houses are really distributed along a one-dimensional structure, or pretty close, a bunch of these lines going around. So here's this thing. Come on, cursor. That's why it's a cursor. It actually has a structure that is a dimension of about 1.6 in the plane. There's some sense in which it seems to try to fill circles, but there also are large gaps. And this is random points from a two-dimensional Cantor set that gives you a pattern with a similar feel. So we did this back around 30 years ago. We didn't quite understand why. We still don't really understand why. Frank Caserta looked at the dimension of branching processes from neurons. And it's hard to find his pictures now, but it turns out that if I look at instructions to grow arborization with neurons, wow, if I could just say, grow it like a tree, have these processes grow out into space like a tree, and you can describe the physics, then I can get something which has a lower dimension than 3, if I think of these as lines and not solid objects. There are gaps, and in microcolumns, neurons can just intermesh and connect. You can get highly connected microcolumns by just instructions that say grow in this way. And in fact, a very recent paper from Scientific Reports, and it's just a couple of weeks ago, how neurons exploit fractal geometry to optimize their network connectivity in the brain. And the key is that they're very simple instructions here. The instructions actually, you can carry out this process by what's called diffusion limited aggregation. Imagine tiny quantities of a neurotransmitter. I don't mean the several hundred microliters of the Pfizer COVID shot. I mean quantities that are so small, I want to consider individual molecules going. And I said neurotransmitter, let me take a neuronal growth factor. There are a certain number of neuronal growth factors which are around. And if I take these diffusing slowly, and if a diffusing molecule hits one of these processes, it can tell it to grow. Another molecule can tell it to grow. And it turns out that the math of this is just like this physical process called diffusion limited aggregation. Tennis balls bounce randomly around, and when they hit a structure, they stick. There's a guy named Hastings who computed the dimension of this. I'd like to claim it's me, but it's actually my younger son. And it turns out that you get the right answer from this process. And it's a little more complicated than that. That's a physicist's highly idealized model, an ideological model from the ideology of physics too, maybe. Consider a spherical cow is a physics joke about studying these things. But a highly idealized model produces this shape. And this shape allows them to intermesh. And now we come back to a mystery. We don't really know the answer, but I'm going to give you a mystery for maybe some of the people know a lot more about medicine and drugs to talk about. So it turns out that if you try to explain the dimension here of these pancreatic islet centers, they look like they're randomly distributed along the processes of pancreatic neurons. Our pancreas is innervated. We don't quite understand what it's for. Maybe the neuron somehow played a role in the islet formation. It's actually a fair amount more complicated, as Julian Smith and colleagues said, but that may in fact be a partial determinant of the structure. Bruce and I Bruce left for Washington when I was still in New York before we got to investigate that question. And weren't quite sure how he would do it anyway, but maybe that's what's going on. And then the mystery that I pose is most women do not develop gestational diabetes. They quickly develop enough additional beta cells to meet the higher metabolic demands. So something's going on in terms of neuron of islet, beta cell and islet, either hypertrophy, either I grow larger islets from something, the beta cells doing something, or maybe I grow more islets. And this is just the dimension here from apical and basal processes in a two-dimensional version. If it were straight diffusion limited aggregation, I would get 1.5 here. And a group, I forget the name, redid the work Bruce and I did with a fair amount more accuracy in 3D, and it's all consistent. Here are some fractals in art. This is a wonderful book by Ron Eglash that looks at designs of some African weavings and Muslim Islamic geometric art, and argues that you see fractal patterns naturally there. Here is a fern branch that has at least for a while, a sort of fractalish structure. Jackson Pollock's paintings have been largely studied in terms of fractal characteristics, and one has discovered some fake Pollocks, and it's not completely random. And this is simply a photograph of a tree, all of this from an article in the Smithsonian. A tree that shows some of the branching. And it turns out what people have studied recently, the science behind this, is that we seem to find and identify structure in these patterns. And they're looking at it to try to build retinal implants that might restore vision. It turns out that there's an awful lot of early visual processing going on to get the potential bandwidth from our eye looking at a signal in space at, well, I mean, we can distinguish roughly 20 or 30 updates per second, but we've got in the megapixel range. And how do we calculate everything? We don't really. What's the structure and how do we make it work? There's Lisa Feldman Barrett argues that essentially it's a Kalman filter, a nonlinear Kalman filter process. We use novelty filters to look at deviations from what we predict. But at any rate, fractals abound in nature and in a bunch of art. We find many of them pleasing. I mean, we may have different tastes in art, but I will tell you that if I tried to randomly splatter some paint and say it's a Jackson Pollock, I would be laughed at. And this is the best I can do on a fractal tree. But at any rate, there's this repeating pattern. And with that, I want to thank everyone for their time, and I'll take questions and discussion. And for people, just look at drawing these things. There's an awful lot there. And you can go back to the Koch snowflake. You can look that up, and you could draw the bumps and randomly in or out and get some even more intriguing patterns. And right now we have the math to understand them. And we see that they're sort of ubiquitous. And so in some sense, we've tamed the monster from 1850s. And I'll stop there.